this mu jet. So at inversion point, this mu jet is 0 because this is nothing but the slope of this isenthalpic curve. Okay, for a given P, I, and of course Ti is already fixed, as I said. For this whole plot, I have fixed the Ti. Although there is no set rule, see, you can do the experiment where you can vary both Ti and Pi. That's fine. Doesn't matter. Okay. Remember this, that you are not supposed to fix Ti just as a, as a, what we can say, a very well organized set of experiment. You don't want to play with too many parameters. At the end, what matters is whatever Pi and Ti you have fixed. Whatever Pi and Ti you have fixed, accordingly there will be a Hi. And Hi is going to equal to H out. Okay, and obviously this gas will open at some pressure Pi, which is less than P, which is less than Pi, and T can be greater than Ti, and T can be less than Ti also, right? So this is all cooling regime, and this is heating. That is marked here. Okay, and that's why I define this Joule-Thomson coefficient, which is nothing but dou T by dou P at constant H. With this, now we'll dive into the problems. Okay. So, as I said you that today we'll only solve problems. If you remember, we have discussed this molecular interpretation also. Just in brief to recall things so that you don't forget. That what molecular interpretation we have given is as follows. That when you are in this low pressure regime, when you are maintaining the gas at low pressure, roughly here, right? We exit, of course. Then what happens? That when gas is expanding at this low pressure, the molecules are relatively far from each other. Far in the sense, you have to see this curve. So if this is distance and if this is molecular potential energy, then your distance between molecules, intermolecular distance, is in this regime here. And in this regime, attractive forces dominates. Okay, so if your gas wants to expand, because since you are forcing it to expand by maintaining a low pressure, then in that case the gas has to overcome this attractive forces. And since there is no work transfer, there is no heat transfer, gas will try to extract energy from itself, and hence that energy will be extracted from that what we know as average molecular kinetic energy. So from there, energy will be withdrawn so that these attractive forces can be overcome. And since you are cutting some part from the average kinetic energy, molecular kinetic energy, temperature goes down. On the other hand, if your pressure is very high in this high pressure regime, if you are maintaining high pressure regime at the outlet, provided that this P is less than Pi, no doubt, but P is relatively higher with respect to lower P, then in that case molecules are very close to each other, and it depends on the nature of molecule also. Don't think that it only depends on what pressure you are maintaining at the exit. It also depends on what kind of fluid it is. There are very van der Waals gases, Ping-Robinson gases. We will see that in very briefly. We will see as a last topic, and then Professor Gargilas will take from there. So at high pressure regime, what we said is that these molecules come very close to each other, so close that in this domain where repulsive forces starts dominating. Once there is a repulsive force, you can imagine this phenomena that you have two charges of same nature, means same sign, and if you bring them closer, they will repel each other. So you have to hold those charges. Once you free these charges, they will repel each other. So what will happen is that repulsive potential energy will decrease, and it will be gained as kinetic energy. Same thing is here. The distance is so close between molecules that repulsive forces dominates, and due to which, of course, these gas can expand easily without any expense of energy, and there is some release of energy also through this repulsive nature, due to this repulsive nature, and that will be gained by the molecular kinetic energy, and temperature increases. That is called heat effect. That is molecular interpretation. Okay, that's all. Now we are going to problems. So first problem, so first problem which we are going to do is on refrigeration cycle. Okay, this is refrigeration, specifically vapor compression cycle. There are other kind of cycle also, but overall the concept is same. Okay, why we are going through this refrigeration just after throttling? Because we know that throttling is a process where it is possible to cool down a gas or a fluid that we have seen. For a particular range of temperature and pressure, we can obtain this cooling effect. Okay, and that is the whole I mean, that is the basic you can say basic unit in any refrigeration system, the unit which I am going to discuss. So which is as follows. I am sure after previous class probably have checked your fridge that whether there is a throttling device or not. If not, please check it. Anyway, so what happens in the fridge? So there is a evaporator. We start from here. So this is called evaporator. Okay. So from evaporator, let's say heat is coming in. Here heat is coming in. We'll see the nice schematic. Okay. So from where heat is coming in? Whatever you have kept in the food. So that's why there is a fan in the fridge also, so that there is air circulation. So what air will do? Air will extract heat from this. Why air is extracting, that will be very clear soon. Because okay, let's see. So this is a evaporator. From here, from this evaporator, since heat is coming in from the food item, okay. So this is actually liquid vapor mixture in evaporator. Okay. Then this vapor enters to a compressor, mechanical compressor. What is meant by compressor? We do extra work, soft work. Okay, soft work. And due to this soft work, we can compress the gas. Okay. So we are so the gas is entering here. We are compressing the gas, and once we compress the gas, then so when we will compress the gas, what will happen? That if it is let's say mixture of saturated liquid and vapor, it will be more saturated liquid, right? Or its quality will decrease. When you will compress a gas, if let's say this is X1 quality here, and this is if quality X2, we are maintaining quality X2 here, then X2 should be less than X1. That's what we are guessing. Okay. Sometimes you'll see in the problems that it is directly written that from here saturated vapor is coming out. I mean, depends. Okay. Now this claim will not be right. Let's move. I'm not sure. Okay. That it depends on the enthalpy and temperature, pressure, condition, whatever. So here we compress. We'll see through the problem. So right now, don't claim anything. This is compressor. Okay. Once so when you are compressing the gas, its pressure increases. Okay. Then this compressed vapor passes through a condenser. Okay. Compressed vapor passes through a condenser. So when it passes through a condenser, then what happens? That there is it's a heat exchanger. Okay, a condenser is nothing but a heat exchanger. So here, what will happen? That whatever heat was this whole vapor was carrying, okay, that will be taken at this condenser. So basically, basically this condenser is open to atmosphere. Okay, so what will happen here? That here through this heat exchanger, this heat will be taken. So here heat goes out. Basically, what happens that here vapor condenses. Very simple. And when vapor condenses, there is a heat release, and this heat goes outside. Okay, outside means in your room, wherever fridge has kept or refrigerator has kept. So it will go out. Okay. Then once it loses heat and it's getting condensed, we have this saturated liquid. Now this saturated liquid will be throttled. Okay, and once you will throttle it, what will happen? It will again cool down. So after throttling, cooled liquid, okay, or cooled liquid vapor. So this cooled liquid vapor, because you are expanding the gas, so there is chance of that there is some vapor formation also. So after throttling, whatever mixture you are getting, that is cooled, and again when it will pass through evaporator. Why we are saying it evaporator? What is happening? See, the in this section a cool liquid vapor mixture is entering. If it is cooled, that mixture, it will try to and here your food items, let's say you have brought something from the market and you just kept it in the fridge, so its temperature is higher. So whatever air will come into the contact of this, whatever air is circulating in your fridge, when it will come in contact with these food items, okay, that air will also become hotter, and that hot air is interacting with this cooled liquid vapor mixture. What will happen? That will extract heat from the gas which was circulating inside the fridge. So once it will extract it from the gas circulating inside the fridge, the gas will cool down, and once the gas inside the fridge will cool down, it will extract it from your food item. So that's how your food will go to the lower temperature. So basically what is happening, that in this step we are extracting heat from the food item through air. Air is just a medium. So cooled liquid air enters in this unit, okay, and it extracts heat from the food items. Once it will absorbs heat from the food item, then again there is some evaporation, okay. That's why this unit is called evaporator. And then since you are taking heat from this, there is a chance that everything can go to vapor. We don't know. Everything can go to vapor, or it can be a liquid vapor mixture, doesn't matter. So again same thing. So this cycle is keep on running, okay. So again let's try to understand from the schema. First I would like to run this animation, and then I'll show you the the bit easier schematic, so that you can understand this concept easily. So let me first show you this. So you can see this wait, and maybe I can open up press page. So I'd like to show you the lower one, how it works actually. So you focus on this right bottom diagram. What is happening? Oh, I can hide this top sharing. Right. Now you can see that the food item. So you can see that this, ignore this top arrow, this top arrow animation, the arrow which is going up. That is by mistake in this animation has been kept. What I am trying to show, that heat is getting extracted in the evaporator, means down, okay, and then that vapor enters into this compressor. You can see this compressor is compressing the gas. Once it gets compressed, why we compress the gas? So that its pressure increases, okay, and of course enthalpy also increases, because you are working on the gas. Rather than pressure, we should say enthalpy increases. So we will see the equation. Through equations we will get a better understanding what is happening where. Then this compressed mixture passes through this heat condenser on the top, okay, where it gets condensed and heat is getting released outside the fridge or refrigeration unit. Then this mixture travels, it goes through throttler, and we know that in throttling we make sure that we are maintaining inlet and outlet temperature and pressure in such a way, means Ti, Pi and Pe, that it cools down. So this cooled mixture comes to evaporator. In evaporator system, what is happening? Heat will, since it is cool liquid, it will try to extract heat from food item through the air inside the fridge, okay, and this way heat will extract it from the food item, and it will be sent out at the top at heat exchanger unit, okay. So that is the rough mechanism. And where is our, I'm sorry. Yeah. So that is the rough schematic of real fridge, okay. If you want, you can check. Of course, I think you have seen such kind of So if you'll see, I'm sure that you have seen such kind of bars in your fridge, in all fridges. I'm sure you have seen it. This is nothing but condenser. Here your this compressed liquid vapor mixture gets condensed, or saturated vapor, whatever it is. We will see what it should be. Okay, right now I'm not claiming anything. I guess enthalpy is increasing, so it should be a saturated vapor. So whatever it is, here heat will be released into the environment because that vapor will condense. Okay, so here Q is going out. Okay, so then it should enter through a throttler. So where they have pumped, okay, they have skipped the throttler in this diagram. Here there should be some throttler. Okay, so after condenser there should be some throttler. Make it properly. Let's say that's how we show throttler. So then it passes through throttler. Once it get this mixture get throttled, it cools down, and then it will go through this. That's where you keep your food items. Since this is a cooled gas, it will take heat from that unit. Okay, from those food items. So once it takes heat, more and more liquid will go to the vapor form, and then this liquid vapor mixture go to a pump or a compressor. Its pump is not a correct word. We should say compressor, because we have a real fluid is a mixture of gas and liquid. Okay, so that's how this fridge system, this refrigeration works. Now I'll draw a better schematic so that you can draw it. Okay, just this animation I have found it on internet, so I thought I should share it with you. So is it running? Oh no, so there is no animation in this. Here I have kept this that TS diagram, so that you can see later. Let's now try to draw a very nice. So let me draw it for you, that when we want to draw such system, then how we should draw it. Okay, so here first, okay, let's take. So here first we have a evaporator. Okay, this diagram will help you because it's very fast, and since it's a schematic, it's easy to draw. So we have evaporator. Okay, then from evaporator it goes to a compressor. So this is compressor. In compressor, what we do, as you have seen, work is done from the external agent. Okay, then this compressed mixture will go to condensation unit. Okay, why we are not saying it heat exchanger? Because it is exchanging heat with the whole surrounding. Generally in heat exchanger you have one inlet, there are two fluids, but here the one unit is this liquid vapor mixture. Okay, this compressed vapor, and surrounding, it is losing heat to the surrounding. In that case we call it condenser. Ultimately there is a heat exchange here. So once this compressed gas condenses, heat will go out from here, okay, to the environment. So Q is going out. This is condenser, and then from here you send it to a throttling unit. There are various signs to show throttling. Sometimes people show by this sign also, throttling. Okay, so this is throttler, and then Here you just get this cooled mixture, liquid vapor mixture, which will go through your operator. Okay, so since it is cooled, as I told you, whatever you have kept here, let's say food items, चलो ऐसा करते हैं, अमूल का बटर बना देते हैं. Okay, so whatever food item you have kept, it will take it from there because it is cooled. So and the food item which you have just kept in the fridge, it is at higher temperature. So through the air which we have in this freezing unit, so heat will come from this food item to evaporator, and this cycle will keep on going. Okay, now let's solve a problem on this, and that will make it more clear. So we'll go to problem. Yes, here. Okay, so in a vapor compression refrigerator, saturated. So you can read this question. Just a moment, I'll take a break. So what we have, that in a vapor compression refrigerator, saturated Freon 12 at, okay, so before we go solve this problem, it means we always need a fluid which is running in that closed circle. Okay, that closed path. Okay, so have you ever heard this, many of you, that the gas of fridge at the refrigerator has leaked? Have you heard this? Maybe from the person who comes to a house. So that is, so when you say gas is leaked, means the liquid which runs through this whole cycle, which is responsible for, so you have to take some real fluid, some real gas, which can be liquefied. Okay, so that gas, that fluid gets leaked. Once fluid gets leaked, there is nothing which will run in that, that circle, in the, whatever we have seen, this cyclic process. And that's why that fridge stops working. That is one reason. Probably your throttler has damaged. That is also, so gas is full, but let's say throttler got damaged. Once throttler got damaged, then it will not, because you will not get a cooled gas, and then it will not suffice your purpose. Okay, so the main ingredient, if you will see, is actually throttler, because once you have this cooled liquid vapor mixture, that cooled liquid vapor mixture extract the heat from your food items, and then it carries, and then it go to condenser through compressor, and then it get condensed and releases the heat to the environment. Okay, okay, fine, perfect. Now let's solve this problem. That will make it more clear. So in a vapor compression refrigerator, we have saturated Freon as liquid. I don't know in these days what liquid or real fluid has been used in the refrigerator. You can check, just as a knowledge. In an interview, one can ask, you are a chemical engineer, so do you know in these days which refrigerant is generally used, or which is recommended? Because maybe that that liquid is not environmental friendly, so something like this. So today there are many, in these days there are many such using some such kind of complex chemical species. There is a lot of clearance you have to take. Okay, so you can check that in these days what liquid is being used. Refrigerant, we can call it refrigerant. Okay, so saturated Freon as a refrigerant at minus 20 degrees Celsius, 0.8 enters an adiabatic compressor. So before we solve, let's draw a schematic quickly. Okay, so we have evaporator, then it will go to a compressor, then it will go to condenser, then we'll go to condenser, and then throttle, okay. Throttler. So what it's saying, that saturated Freon at minus 20 degrees Celsius and quality 0.8 enters an adiabatic compressor. Okay. So that Q is 0. Okay. So let's note down first. So here, what is getting entered? Okay. Say it 1. This will be our 2, 3, 4. So at 1 we have what? Freon at minus 20 degrees Celsius and quality 0.8. So of course it's a mixture of saturated liquid vapor. Okay, and that is obvious also because here you see from food item we are extracting the heat. Food items. So since you are extracting the heat, more and quality will increase. So you have some quality, let's 0.8. Okay, here, and then this mixture enters in the adiabatic compressor. And what we do in the compressor? Yes. So we do extra work. If you remember the concept of compressor, we do work from outside. Okay. So how we do this work? Let's see who will tell us. Just to interact. So Shravya, what do you think? Shravya. Hello? Yes, Shravya, you can hear me? Hello? Shravya? Okay, Shravya. Just let me mark. Okay, Deep Joy, you can hear me? Deep Joy? Deep Joy. They are in the class, but probably they have just came online and they don't care. So I also don't care. So you can inform them. I'm a bit serious in this regard. If you don't want to listen, it's better you don't join. I don't mind. There is no marks for attendance. But if you are here and just playing with the system, we all know that this online mode is because there is no other way. And if you're coming online and then doing something else, this is really not acceptable. So I'm calling again the name and you can inform these guys because I can see that they are in the meeting. Shravya, Deep Joy. Deep Joy and Shravya, if you can hear me, please respond. Either through chat. I don't think there is any connection problem. So I'd like to hear from both of you. Fine, no problem. Okay, guys, let's move. Anyone? We cannot waste time here on this. I know how to handle such cases. Yeah. So anyone that this what we say this work done. Okay. So in compressor we do. So how this work is being done on the compressor? What is the source of this work? Anyone?
Sir, there is something rotating fan like thing.
Yeah, true. I got your point. Like what energy? Through what? In which form we are providing the energy for this work? That's what I'm
Electrical energy.
Electricity, right? That's where your consumption, like you are giving it. So here we through electricity. So basically through this current, as someone said, that this piston system or whatever rotor system, rather than rotor, we should say this is a compressor, right? So it's simply a compressor unit. Like there is a piston which will compress there, and this piston is of course connected to a motor. So that through that motor, that rotation motion, you will convert it into this, or there can be this rotary type of compressor also. Rotor, you have seen that we have seen the design of compression. That due to the design of the blade, gas gets compressed. Anyway, in any by any way you are compressing the gas, but how you are doing it? Not manually. Like you will provide the electricity to the motor, and through the motor there is a system which will compress the gas. So here is the energy consumption from our side, and that's why you pay electricity bill. Okay, so you compress the gas, and then at stage 2, what we have, that it's saying that it leaves the adiabatic compressor as a saturated vapor at 42 degrees Celsius. Since nothing is mentioned and it's only saturated vapor, what I will assume quality is what? Anyone? Nothing is written. So what I should
1.
assume? 1, because nothing is written, so I will assume that x equals to 1. So once it comes out of the compressor, its quality is 1 and temperature is 42 degrees Celsius. Okay. So basically, what we are doing here, when you are working on the fluid, the overall enthalpy increases. You see, there is increase in temperature, so its U will increase. Okay, and overall quality has increases. Fine. So once we compress the gas, its enthalpy will increase, and that we'll see through a. So now let's do this calculation from 1 to 2. Okay, that so first complete this. Okay, so the refrigerant leaves the condenser as saturated liquid. So this will go through condenser, and since our quality was 1, what it has written in this problem, that it is completely getting going into the liquid phase. So from here, let's say if we say stage 3rd, what we are getting is saturated liquid. So quality is 0 now. Saturated liquid at 42 degrees Celsius, and then this liquid is getting throttled through this throttle device, and when it is coming at this when it is coming out from the throttler, what is happening, that further throttle to a low pressure refrigerant having temperature minus 30 degrees Celsius. So temperature here is minus 30 degrees Celsius. Okay, and pressure we don't know, so let's say it P4. So what is, as you asked, determine the pressure to which the refrigerant is throttled. Okay, so we want to know P4 and also estimate the power input into the compressor. This what we need to know. What are the unknowns? What is P4 and what is WS dot? At what rate this compression, this refrigeration unit is consuming energy? Okay, so that is the overall description of this problem. Let's solve it quickly. It's not very difficult. Okay, so first of all, what we should remember that let's start from this compressor unit. Okay, so we know that for compressor, if you see the first law, that energy equation, okay, there is no heat transfer. The only thing we are transferring is this work transfer. Okay, fine. So and then we ignore the delta K and delta P, that macroscopic potential energy and macroscopic kinetic energy. So if you ignore these things, then if you remember, when we have written the equation of compressor, we have discussed it in detail. The equation which comes out to be, so if you write here, H2 minus H1 is equal to what we write, H2 minus H1 is equal to minus W dot S by M dot. You can check in your older slides. I think it should be right, because H2 will be, so if you write H2 will be H1 minus Ws dot by M dot, and since W dot S work is being done on the system, W dot S will be negative, negative, positive, so your enthalpy should increase. That's what we expect in the compressor. That why we compress the gas, to increase its enthalpy. Okay, so if someone asks you why we compress real fluid, the crisp and best answer is to increase its enthalpy. You are working on this and its enthalpy will increase. Okay, fine. So let's solve this then. If we know H2 and H1, we can calculate this rate of work done. Okay, on the means the power input to the compressor, Ws dot. M dot is already given. So H2, of course, H1 we can do. So what we have to see, the Freon table, right? So I hope it should be in your book. If not, it's available on internet. So if you will see here at minus 20 degrees Celsius, we'll check. I'm just writing it for you. If you'll check, then P saturated. Since it's a mixture, we know that if temperature is fixed, P is also fixed because its quality is 0.8. So P sat comes out to be 150. I have noted down for you just to save the time. 0.83 kilopascal. Okay, and I'm not going to. So of course we have to. All you need is HF, Hg. Okay, HF is 17.95 and Hg is 178.9. Okay, so I will calculate here quickly. Anyone? I'm not going to solve it completely. Just if you know, and then you can do it. I'll write on the fine. How will calculate H here?
X into Hg plus 1 minus
Yeah,
X.
that you know. Thank you. That's so. Here H1 can be calculated. That you know. Hg x. Now you guys are quite comfortable with this, so I don't have Hg into x. I don't need to worry about this so much. HF 1 minus x. So let's say H1 is done. Okay. Then we go to H2. Now H2 is also a saturated vapor. So it's a saturated vapor and quality is 1 at 40 degrees. So H2 also can, H2 will be simply here. Yes, Bhavna? H2 will be what? Hg directly, right? At 42 degrees Celsius, right? It's a, we are saying quality is 1. So we know H2 also. There is no place here. So what I can do, I can write H2 here. H2 is nothing but Hg at 42 degrees Celsius. That you can check. So I have not written it. That value I have not noted down. But I think it's very trivial. I mean, you just need to see the table. So once you know H1, H2, and once you know, okay, I think I have written somewhere. Let me write it for you. At least one problem I should solve on this representation, right? So H2 should come out to be, where I have written it, just a moment. I think H2 comes out to be 203, means H2 is nothing but Hg at 203.75 kilojoule per kg. Okay, kilojoule per kg. So you know H2, you know H1. Okay, H1 I also have calculated. So let me write it for you since I have calculated. So H1 comes out to be
146.7.
yes, perfect. Yeah, one very good. Thank you. This comes out to be, let me use a different color. It's just a formula fitting problem, nothing very. So H1 146.71, right? Okay. So you know everything, you know m dot, you know H2, H1. So if you calculate this rate of work done, this W dot S comes out to be, according to me, it should be with a minus sign, of course. Or if you want to say power input, you can remove this minus. Okay. Ws dot will come negative, but since in the question it has been asked that estimate the power input. So from your point of view, this much positive power you have to provide. So that comes out to be 50 rather than Ws dot. So you write it minus and then wait. So W, we can say this way, na? Power input is nothing but minus of Ws dot, which will be equal to 57.04. Is it matching? That's what you getting? Kilowatt.
Yes.
Yeah, perfect.
Yes, sir.
So we have solved one part. Now another part is asking that determine the pressure at which this gas is getting throttled. What is P4? Okay. So for P4, what we will say, can anyone give a hint that it is getting throttled? So what you would like to do? Anyone wants to give some hint?
Isenthalpic.
Yes, very good. So we know that simply. So if for this here, for this unit, H3 is equal to H4. Yeah, that's all. Nothing else. It's isenthalpic process. So just before and after throttling, enthalpies are equal. So H3 we can calculate because see it's a saturated liquid. Means X equal to 0 at 42 degrees Celsius. So can anyone tell me what is H3? I have noted it down. Let me see where. So H3 is, since it's a saturated liquid with so it's yes. So for this it's 77 point. You can check also. This is 77.146. So H3 here, H3, it's a saturated liquid. So this is 77.146. Okay. Can anyone check if your friend table? I think so. That's what I have noted down. I think it's fine. You can check it later. Then what about H4? Sneh, what about H4?
H4 will be same as H3.
No, but then we need to find out the pressure at which it is getting throttled. So what do you think? What will it be for?
So in Freon table, we will see for
Yes.
like
It's a
temperature minus
saturated pressure.
yes, enthalpy is H3. Then we
Yeah.
will find pressure.
So basically, you're saying it's a saturated pressure, right? That's what you're saying, right? P4 is nothing but the saturated pressure.
Yes,
That's
sir.
what, okay. So since it's getting throttled, we will get a liquid vapor mixture. Okay. So since we'll get a liquid vapor mixture, let's see that there is no mistake. We know H. Okay. Yeah. I think since we are throttling it, it will be a liquid vapor mixture. Okay. No doubt. So what is the pressure? So we have to. So this P4 is nothing but P sat at minus 30 degrees Celsius. Okay. So that we have to check, and that at that pressure you are throttling the gas. So that you can check. And one more question can be added, that what will be X here? What is X here? So I will calculate that, Sneh. So we know H3, right?
We know H3, right? Yes,
Yeah.
sir.
And H4, what we'll say? Let's say if at 4 this is from Freon table we can calculate Hg4 and HF4, means at this minus 30 degrees Celsius. So you can calculate H4 also, right? That Hg4x HF4 1 minus x, where x is the unknown. Hg and HF4 are known. So if you calculate, that x comes out to be, that this x comes out to be 0.4124. You can give a check. Okay, and pressure P sat, if we'll check, is P sat P4 is nothing but P sat at minus 30 degrees Celsius, and this comes out to be 100.3141 kilopascal. Let me check again in the table in my book where I've written it a long time ago. So just let me check that Freon table. So minus 30, yes, minus 30 degrees Celsius, P sat is 100.314. Okay. Yeah, so that's all. So this is the problem on refrigeration unit. So what we should learn from this problem, that in general, so that we don't forget, that in this condenser unit, when we compress the gas, when we do work, its enthalpy increases. Okay, and its overall quality also increases. Right? Because since you are doing the work, then yeah, that's all. I mean, then once it has higher enthalpy, then it goes to a condenser where it loses the heat. Fine. Acha, can anyone tell me that why we are doing this? Why we need a compressor? Anyone? Can you think over it? Why we are compressing it? Now we should think that, okay, fine, why are you compressing it? Throttling understood, but why we are compressing it?
So we are just increasing the pressure because the pressure at 3 should be greater than pressure at 4.
Very good. That is one reason. Perfect. So one requirement, if I go to a fresh page, one requirement is that okay, we have to go back because this. So one requirement is that, as you said, that we need P3 greater than P4, right? That's what you said to do for the throttling, right? Okay, that is one requirement. Anything else? That is wonderful. There is one more requirement. Think about it.
Sir, we need to increase the temperature of
Very
the
good.
gas
Very good.
greater than
Yes.
the atmospheric
The
temperature so
atmosphere,
that
yeah,
the
very
heat
good.
transfers from condenser
Perfect.
to atmosphere.
Very good. Yes, very glad. Okay, so another requirement is that see whatever liquid is coming through that evaporator, its temperature is not so high that it will, in fact, it's quite low. It won't be able to release heat from the environment. In fact, it will start taking heat from the environment. You don't want that. Whatever heat is this evaporator is taking from the food item, okay, that is not sufficient enough to increase the temperature of the gas so much that somewhere it can go and lose the heat. Heat transfer will only take place if your fluid go to a higher temperature, higher than the atmosphere. And that's why you have to compress it here so that its temperature increases so much that it is higher than the ambient temperature. Okay. So once it goes to this 42 degree, then whatever heat it is carrying with it, that will go to the environment. Okay. So due to these two things, we need this compressor unit. Okay. You can think more on this. Probably more doubts can come. Means why this, why that. We can answer. But overall, this is the gist of refrigeration unit and one problem. Okay. And why I covered this problem? Because see here we have solved the equation of throttler also, which is simply S3 equal to H4. There are assumptions that delta K is 0, delta P is 0, no work transfer, no heat transfer. All such assumptions are there. Then only this equation is valid. But as an engineer, we assume those things that okay, just for the estimate, let's say it's an isenthalpic process. Other things are ignored. Then we have solved here the equation of this compressor also. Okay, that's all. I mean, heat exchanger problems are very easy. Anyway, I think that I have given in the assignment. You can check. If not, don't worry. It's very simple. I will never ask a problem on heat exchanger. It's very, very simple. Okay, with this, we go to another problem. So refrigeration is done. Now this one, fresh page. Okay, let's read this question first and then we'll solve it. So after reading this question, we'll take a break and then you come back and we'll solve it. So we have steam at pressure 20 bar and temperature 500 degrees Celsius. Steam at pressure 20 bar, 500 degrees Celsius is flowing in a pipe. An evacuated tank is connected to this pipe through a valve. Okay. The valve is opened and the tank is allowed to fill with steam until the pressure of the tank becomes 20 bar and then valve is closed. So basically what is happening, that let's say there is a pipeline in which steam is flowing. So this is a pipeline. In this we have steam at pressure 20 bar and temperature 500 degrees Celsius. This is a kind of supply line. Okay. And from here, let's say you want to fill a tank through a valve. Okay. So let's say there is a tank. So this is tank. Right. So initially it's evacuated. Nothing is there. And then you connect it with the supply line and you open the valve. So once you open the valve, steam will go inside it and you have to fill it until the pressure of the tank becomes. So initially, if I write Mi is 0. Okay, there is nothing. Finally, the pressure of the tank PF, okay, PF tank, that also becomes equal to 20 bar. Up to that point, you have to fill it. Okay. So determine the temperature of the steam in the tank at the end of filling. That is the question has been asked. Assume it at adiabatic process. So let's say it is covered from all sides. And you have to neglect the K and P, macroscopic. Okay. This problem we are going to solve. This is called charging of a cylinder. Means you are charging a cylinder with a gas. charging of a tank. That will be our next topic. Then we'll see discharging, and then one more problem. And this way, this flow process problems from my side will be over. You can solve the assignments. Okay. Okay, guys, take a break. So it's 9:57. We meet at 10:05. Okay. Thank you. Okay, take a break. We meet at 10:05. Meanwhile, stop sharing so that. So where stop sharing.